we're given that gravity exerts a force negative mg times the j vector. And of course, I vector in the x direction, j vector in the positive y direction in the traditional orientation, where the x direction is horizontal, the y direction is vertical. So the negative y direction would be downward, and that is, of course, the direction in which gravity accelerates things in this region of the universe, this very small region near the surface of the Earth. Okay. Now, if there's a displacement, delta S sub x times I, in other words, some displacement in the x direction, and some displacement delta S sub y in the y direction, and our displacement vector would be delta Sxi plus delta Syj, that we want to calculate the work done by gravity as an object of as the object of mass m travels through this displacement. Now you can think of this as a mass moving along an incline, so that delta S would be a displacement in the direction of the incline. The angle of the incline would, of course, be the arctangent of Sy, delta Sy over delta Sx, but we don't need that if we have the information on the x and y displacements. Okay, so what is the work done? Well, the work done is the dot product of the force and the displacement. So the work done by the gravitational force, not the work done against the gravitational force. In this case, we're calculating the work done by the gravitational force, is going to be the dot product of the gravitational force, negative mgi, mgj, dotted with the delta S, the delta Sxi plus delta Syj, and that's just going to be negative mg delta Sy. So the work is negative because gravity, the component of gravity that does the work is in this direction. The gravitational force is in this direction. The component of delta S parallel to the gravitational force is in the upward direction. So we're multiplying a downward vector by an upward vector, essentially. And it turns out that, of course, since j dot I is 0, the distance we move in the s direction has no effect whatsoever on the amount of work we do, or the amount of work done by gravity. Another connection is that we can project this gravitational force vector onto the direction of our delta S vector, and we get this projection vector here, the projection on delta S of the gravitational force, and that's just going to be this vector that's depicted by, well, it's going to have a magnitude equal to this leg of this right triangle here. And if we multiply this projection of the gravitational force by the entire distance of the displacement, and note that we have a negative, that our projection is in the direction opposite our delta S, we're going to get exactly the same thing. And that's something you should work out. But what you want to understand at this point with this problem is how this very elegant calculation gives us our result that's consistent with all our intuition. Now there are four situations. Delta Sx could be negative. Would that make any difference in the result? Delta Sy could be negative. We could be moving down an incline. Would that make a difference in this result? And what would the interpretation of that difference be, if there is one? So you want to think through those ideas, but it's going to be very easy to complete this calculation. I'll add that if we take the dot product of this projection vector, and I just put this arrow here, so if you didn't see it before, it wasn't your imagination. If I take this vector here, this projection vector, which I'll just abbreviate PROJ vector, and dot it with delta S, the magnitude of that product, since the two are in the same, along the same line, the magnitude of the product will be the magnitude of the projection multiplied by the magnitude of delta S. And since the projection is in the direction opposite delta S, the result will be negative. And it turns out that this result is going to be, again, negative mg delta sy. So if we just take the projection of this vector and multiply it by delta s and keep the sign straight, as I said before, it works out. I'll also say that we could have projected delta s on the gravitational force vector. We'd have had to extend the gravitational force vector out here, and we'd have projected the delta s vector back along here, and we'd have gotten the projection of the delta s vector. And if we multiplied that, of course, the projection of the delta s vector in the vertical direction is just going to have magnitude delta sy, but if we multiply that by the whole force here, again, we get the same result if we're careful about the signs and the directions of these vectors.